Hello everybody. Today we look at the boundary conditions of electric field and magnetic field across the boundary. Actually, the equations across the boundary between two different media. Okay, so we take two different media and there we see how this electric field and magnetic field is changing. We also see the change, the variation in D, the displacement current, and H. Okay, so we are going to see the boundary conditions for these four quantities: the electric field E, the magnetic field B, D, and H. Okay, for that what we first do is we convert the Maxwell's equations, which we wrote in differential form, into the integral form. Okay, we are writing it in integral form. The first equation is for D, del dot D equal to rho f. Rho f is the free charge density. So integral volume del dot D. If I take integral volume del dot D, d tau. So we are considering a volume integral. So on the right hand side we have the volume rho f d tau. So this one, integral volume rho f d tau, that is the charge enclosed, the free charge enclosed. Okay. So integral volume del dot D d tau, that we convert into a surface integral, a surface bounding this volume, that is integral surface d dot ds. Del dot D now becomes d dot ds. Okay, and on the right hand side we have the charge enclosed. So this is the first equation converted into integral form. Then we have the del dot B equal to 0. Again we take the volume integral volume del dot B dV equal to 0. Then as we did in the previous equation, we convert it into surface integral surface B dot ds equal to 0. Okay, so we converted the second equation to the integral form. Then we have third equation, del cross E, curl of the electric field equal to minus dou B by dou T, the Faraday's law. So to convert it into integral form, we take the surface integral. Okay, we take the surface integral surface del cross E dot ds, that is equal to minus d by dt of integral surface B dot ds. Okay, we can write this partial derivative as the derivative d by dt, because this will not, the ds is not affected by this d by dt. Okay, so it is possible for us to write this as minus d by dt instead of dou by dou t. So here we have the del cross E dot ds surface integral. Okay, so by Stokes theorem we are converting it into line integral. In the first two equations we converted volume integral into surface integral. Here we are converting the surface integral into a line integral, which is integral E dot dl. Okay, del cross E dot ds, that is integral E dot dl, that is equal to minus d by dt of integral surface B dot ds. Then we take the fourth equation, del cross H equal to jf plus dou d by dou t. We take the surface integral. Okay, surface integral of this equation. So integral S del cross H dot ds, that is equal to integral S jf dot ds d by dt of integral surface integral of d dot ds. Okay, and as we did in the previous equation, we are converting this del cross H the surface integral of del cross H dot ds, that is converted into line integral. So we have the line integral H dot dl here, and this one integral surface jf dot ds, that becomes the current, the free current, because what we have is the current density, the current per unit area. So that we are taking the surface integral, so we have this IF free current, and then we have d by dt of integral surface d dot ds. Okay, so we have converted all the four equations into integral form. So this is the first step in arriving at the boundary conditions for the electric field, magnetic field H and D. Okay, now let's see the boundary condition for D. Boundary condition for D. See, we have two media 1 here, media 2, and this is the boundary separating the two media. So to find the boundary condition, we consider a pillbox, Gaussian pillbox. Here we have used this concept, this idea at several places. A Gaussian pillbox is considered here, a very thin pillbox, and it extends equally to the two medias, the media above and below. Okay, and its curved surface is considered to be, very narrow, because its thickness is very small. So this curved region is considered to be very, very narrow. So we need not actually consider the curved surface, only this upper and bottom surface. So we consider the upper and bottom surface S1 and S2, and on this surface, of this Gaussian pillbox, we determine this integral surface d dot ds, the first equation. The first equation, we have to take the surface integral of d dot ds. So that we take here integral surface d dot ds, that is equal to the charge enclosed. So the upper surface, we have this d1 dot ds. Okay, d1 dot ds. Okay, and for the bottom surface, we have this d2 dot ds. And here we have a negative sign, because ds here, it is in the upper, its direction. Say ds is the area of the upper portion or the top surface, and it is pointing upwards. And for the second surface, ds is pointing downwards. Okay, ds point downwards, but we are taking ds, the direction of ds is upward direction. So here we have the negative sign. Okay, negative sign here. So for the upper surface, we are having d1 dot ds. For the bottom surface, we are having d2 dot ds. And on the right hand side, we have sigma f, the surface charge density. We have to find this qf enclosed, isn't it? Qf, the charge enclosed by the surface. We have to find the charge enclosed by the surface. So that is equal to sigma f into ds, sigma f ds, because that is the area of the surface, the upper and bottom surface. So the charge enclosed will be surface charge density sigma f dot, or sigma f ds. And now here d1 dot ds, I can write it as d1n ds. So what is d1n? d1n is the normal component. Okay, we are taking d1 dot ds. This is the direction of d1, this is ds. So d1 dot ds, what is it? d1 ds cos theta. And what is theta? Angle between d1 and ds. So this is d1 and ds. Okay, d1 dot ds, d1 and ds. And this is d2 dot ds, that is d2 and ds. So that is equal to sigma f ds. Okay, so we can cancel this ds. So we have this d1 n, d1n can be also written as d1 perpendicular, and d2n can be written as d2 perpendicular. N stands for the normal component, normal to the boundary, normal to the boundary. So d1 perpendicular minus d2 perpendicular, that is equal to sigma f. And this d1 is epsilon f e1. We know d equal to epsilon e. D equal to epsilon e. So this is equal to epsilon 1 e1 perpendicular, and d2 is epsilon 2 e2 perpendicular and sigma f. So this is the boundary condition for the displacement vector. We see the normal component of the displacement vector is not continuous. It's not continuous across the boundary. It is equal to sigma f. d1 perpendicular minus d2 perpendicular is equal to sigma f. Okay, since the right hand side is not 0, we can say the normal component of the displacement vector is not continuous. Then we have the boundary condition for B. Okay, boundary condition for B. We are taking integral b dot ds, the second equation. We know that is equal to 0. So b1 dot ds, this is for the upper surface, b1 dot ds for the upper surface, and b2 dot ds for the bottom surface. Here the magnetic field is b1, here the magnetic field is b2. So b1 dot ds, it is for the upper surface, b2 dot ds for the lower or the bottom surface. Again, for the curved surface we are neglecting. So we have this b1 dot ds minus b2 dot ds equal to 0. Okay. Now as we did earlier, this can be written as b1 dot ds, that can be written as b1 n or b1 perpendicular ds. This can be written as b2 perpendicular or b2n ds. So that is equal to 0. So b1 perpendicular minus b2 perpendicular is equal to 0. So b1 perpendicular is equal to b2 perpendicular. So b1 perpendicular is equal to b2 perpendicular. That means the normal component of the magnetic field, across the boundary is continuous. The normal component of the magnetic field is continuous. Okay.